Good morning, everyone, and welcome. I'm Dawn Decker, the Executive Director of PCI Mid-Atlantic and one of the sponsors of this program. This is the second of our three-part pre-stressed concrete bridge design seminar, which is being brought to you by two chapters of the Precast Pre-Stressed Concrete Institute, PCI Mid-Atlantic and PCI Northeast. Our last session will be next Tuesday, April 27th, from 11 to 1:30 Eastern Daylight Time. So looking forward to that, and I hope you can join us. To get started with a couple of housekeeping items, please be aware that all folks are muted and will remain so throughout the program as we are a sizable group, but we do want to hear from you via the chat function. So please submit your questions throughout the program. We have allotted time at the end of the session for a Q&A. Additionally, in the handout section, which if you look in the chat function, about 10 handouts have been provided for you to download and follow along. These handouts are various resource guides as well as slides so that you can follow along. You can take notes on those files. Please download those at your convenience and let us know if you're able to download those, as we'll make it available in a WeTransfer link if you're not able to access them. Please know that we are recording these sessions and we'll make them available to you online. PCI has met the standards and requirements of the Registered Continuing Education Program. For you to get or earn credit, continuing education credit will be reported based on your time of attendance. You will receive a link to download your certificate from RCEP within 10 days after the completion of this seminar. Please check your spam box if you did not receive an email. Please know that this program and all of its contents are protected by copyright, and if you want permission to use them, please let us know and we will do so. Now, to get started with our presenters, as I said, I am Dawn Decker, the Executive Director of PCI Mid-Atlantic, and I provide technical and education support to DOTs, design and construction community, and professors in their academic programs throughout New Jersey, Pennsylvania, Maryland, Delaware, Washington, D.C., and Virginia. Reid Castrodale and I share responsibility for the New York City market. There are 14 transportation producer members in the Mid-Atlantic chapter, and these folks provide many valuable services. They provide design assistance, budget development, schedule planning. They will deliver plant tours and other services to state DOTs and their engineering consultant partners. Notice in your handouts that there are actually two references of directories with corresponding products that these fabricators produce. And I have a slide here in a moment that will provide a little bit more detail on that. It's an absolute privilege to introduce Reid Castrodale and the rest of our presenters for today. For the past 30 years, Reid has provided leadership support and education to the New York City market, as well as to the rest of New York State, Connecticut, Rhode Island, Massachusetts, New Hampshire, Vermont, and Maine. Through her Bridge Technical Committee, countless resources, new products, and training seminars like this have been delivered in partnership with state DOTs and her regional partners. Reid Castrodale is the president of Castrodale Engineering Consultants. He provides consulting services specializing in pre-stressed concrete, lightweight concrete, and of course, accelerated bridge construction. He's a registered professional engineer in 3 states. Reid is the bridge consultant for our Georgia, Carolinas PCI chapter. He's the managing technical editor of Aspire magazine, which Rita will talk a little bit more about this in terms of publications in her section of the program. And he is a fellow of PCI. He's been active in various PCI bridge committees for over 30 years. Welcome to JP Binard, who is the owner of Precast Systems Engineering, or PSE, which specializes in construction engineering, primarily focused on precast, pre-stressed concrete for buildings, marine structures, and bridges, while utilizing ultra-high performance concrete in components and connections where possible. JP chairs various PCI committees and has authored and co-authored several papers on UHPC and many other precast, pre-stressed concrete topics. Gorman is the Senior Vice President and Chief Operating Officer of Prestressed, which is located in Roaring Spring, Pennsylvania. Greg has 39 years of experience in the construction industry with the 20 most recent years in the precast, prestressed concrete sector at Penstress and New Creek Products. Again, if you'd like more details about these specific individuals, as well as their contact information, there is a handout that has been uploaded in chat, and you'll get all the information about our presenters in that particular reference. Now on to a few other tools that are there at your disposal. PCI Mid-Atlantic and PCI Northeast have created easy to use, up-to-date transportation producer member product directories. In the Dropbox folder, or sorry, in the chat function, you can download each of these files, product categories in each matrix, and you can see that at the top of the slide here. This is a snapshot of the top of each of these documents. You can see bridge products, piling, precast substructures, and other miscellaneous transportation products. And again, there is one for each one of our respective regions. PCI has recently published a new 2021 Transportation Publications and Online Resources Catalog. This 20-page reference guide reviews the 20 publications and 28 online on-demand e-learning courses available for your professional and academic use. During her session, Rita will discuss some of these specific publications and courses that are available to you. So let's talk about the program today and what are the specific topics that we'll be discussing. Reid Castrodale will discuss basic precast design, draping and bonding, as well as girder sections and camber. Gorman will provide accelerated bridge construction examples. And we had numerous folks request this particular topic when we did a survey after our first program. And Reid Castrodale will provide an overview of transportation resources, including next beam updates. We'll conclude with a question and answer period, which will be facilitated by JP Binard and Reid Castrodale. Note that our last session again will be next Tuesday, April 27th, and we'll discuss different topics. So Rita will cover off on that in a moment. Now over to Reid for our first topic, basic precast design, draping, and debonding.
Thank you, Dawn. We will get set up here and get moving.
There we go. Thank you, Reid.
Yep, thank you. And I think we've had some discussion on the chat box about getting handouts and things like that. Hang on, let me get, I'm not shared yet. There we go. So I don't know, Rita, do you have any comments on that? Or there's been a link that has been shared over there.
I did. There's a WeTransfer link that I just posted. So you should be able to click that link and download all the, there are 10 files that are basically connected to that link that you should download, not only all the notes that Reid is developed for the seminar, but we also have additional resources there too.
Great. Thank you, Rita. All right, everyone, we will get started here with the first of the presentations. And we're going to start with some discussion of basic design. Is my video not on? Can you all see me as well or not?
I can see your slides, Reid.
But I was wondering about my smiling face, but I just see, I don't see that. Well, you don't need to see my smiling face. If, we're going to talk about basic design of pre-stressed girders. And I think I'm at the beginning. Hang on, we're getting a little technical glitch here. Let's get back to the beginning then. Somehow I started at the end. The best laid plans. Okay. We're going to talk about designing pre-stressed girders, and we're going to be talking about PCI Bridge Design Manual to some degree, or a lot of the information that you will be seeing comes out of the PCI Bridge Design Manual. As we mentioned in our first session, this manual is free, so I would highly encourage anyone who does not have it to download it. The electronic version is free. So if you want more information about what I'm talking about today, I would recommend you take a look in Chapter 8 of the Bridge Manual, and also Chapter 9, where there are a number, I think there are 9 or 10 worked out design examples. One thing I also wanted to point out is that Section 5, the concrete structures chapter in the LRFD bridge design specifications was reorganized in 2016. So as a result, a lot of, not all, but many sections moved around within that document. So the changes appeared in the 8th edition. So if you have a specification edition that's the 7th or earlier, some of the references that I may use today will not jive with what you have for your LRFD. So what I have today is using the 9th edition. There are some resources if you ever want to make a conversion from one to the other. Okay, there are crosswalk tables that you can use to get between the old and the new version. I actually had this up earlier this week because once in a while you have to do this sort of thing. So just wanted to let you know that those were available out on the Aspire website and some other locations as well. We're going to talk about design issues initially here. And the first, of course, is what compressive strength do we use? We have two situations we have to look at: the initial concrete compressive strength, and then the final, the initial or the strength at release or transfer, as we call it, is FPCI, as you can see there. Let's see, I'll get my pointer going. And while we rarely use it in girders, we might use it in some other products. That the minimum typical value on that's 4.5 KSI. It would be nice to only go up. It'd be nice for the fabricators if we only went to 6 or 7 KSI for that initial release strength. In some cases, we may have to go higher. We typically specify the release strength as we designers come up with that in 0.1 KSI or 100 PSI increments. That means that we're trying to be as precise as reasonable in specifying that initial strength so that the pre-stressors can get their beds detensioned as soon as possible. They don't have to keep waiting around for the next 500 to come up. It's just 100 is good. So it's important for the producers to do that, to have that opportunity with precision. So I would recommend 100 PSI increments on the release strength. We really shouldn't use strengths that are any greater than are required by design. Lots of times people just say the release strength is 8/10 of the 28-day strength. That's okay, but it really helps, as I just said, the producers if we can back that release strength down and just use the strength that is required, and you can actually back calculate that. If you look at your stresses that are occurring at release, you can back it down and come up with the FPCI that would be required. So I'd suggest you do that as a designer. Doesn't take much time, and it's helpful for the producers. As far as the final strength, 28-day strength, as we typically call it, we can go up to 8.5 KSI. We can go up to 10 KSI. That's pretty much the practical range as far as how high we would want to go. But the pre-stressors will be glad if it's not quite up that high. Those strength increments are generally specified in a 0.5 KSI increment. Generally, the release strength is going to be what governs. So we end up getting the 28-day strength well before 28 days. And usually that 28-day strength is required in order to ship the girders, which in some projects that can be an important thing to hit that strength as soon as possible so they can get shipped out. Of course, in other cases, it may not be so important if the girders are going to sit around for a good while. As I've already alluded to, the higher release strengths can require beams to sit longer in beds. That increases the chance of cracking. It definitely slows down production. It also can slow down field construction schedules if there's pressure to get that turned around quickly, and will affect the price of those girders. Some design approaches can reduce the required FPCI, the release strength, and that's typically draping. If you drape rather than debonding, you may be able to decrease the release strength a little bit more. If higher strengths are needed, higher release strengths, the pre-stressors will deal with it. But we as designers should try to help things out by using the minimum release strength that's possible. And as far as the 28-day strength, as I already mentioned, 8.5 KSI is preferred. We can go up to 10. I would encourage you not just to use high numbers because you can. I know that years ago when high strength concrete first started being used, Nebraska used a design with 12 KSI and many people tried to follow after them. Well, it turns out that that 12 KSI design that was used in Nebraska could have been designed with 9.5 KSI. So they really didn't need to go to 12. They were just trying to prove the concept, but everybody else was trying to follow. So just use what you need. Now, getting into the steps that go on and some of the background that we have prior to or involved in design, probably one of the major things we need to be aware of is the transfer of pre-stress. As we talked about in the last session, pre-tensioned members transfer the force in those strands to the concrete entirely by bond. That transfer is accomplished through surface adhesion, the concrete actually bonding to the metal, the strand. There's also some mechanical resistance from the shape, the twisted shape, the helical shape of the strand. And also there's an effect called the Hoyer effect. It's just like a rubber band. If you stretch a rubber band, it has to get narrower while it's under tension, and then you let go of it and it comes back to its original width. Same thing with these strands. You put them under a lot of tension, and then at the ends, there's no stress. When you're out here past the end of the beam and you detension that strand, this strand has no stress in it. So the strand immediately inside the concrete also doesn't have any stress and therefore will want to expand. And that provides a little bit of a wedging type action that helps with the transfer of pre-stress. Here's just an example. This is some data that I generated when I was working on my PhD at the University of Texas at Austin. So if you take a square prism of concrete with a strand running down the middle, you can measure the strains along the side from before and after release, and you get this kind of variation in strain from the end of the specimen to the interior where you get the effective pre-stress. So that's what's going on with transfer. And this is some actual data from a little prism, just to let you know what it looks like. As far as how we use it in design, this is a schematic that's coming out of the PCI Bridge Design Manual, and it's showing the increase in stress in the strand from the end of the beam. This is the end of the beam right here, as you go into the length of the beam, move inward. At first, you see a linear variation of stress up to a constant value, which is the effective pre-stress in the strands. And that change occurs over the transfer length, L sub T. So this is FPE. So this is what we use for service limit states. Then we move on to the next stage, and that is the ultimate stress in the strands, which is the strength of the stress at the limit state. This occurs at the development length, which comes out further. So there's a continual increase in the available stress in the strands until you get out to the development length, and then FPS is available for the rest of the beam until you get toward the other end and it comes back down again. So These are the two major stresses. FPS, what we use at strength limit state, and FPE is what we're using at the service limit state. And just to note, the transfer length, L sub T, is included in the development length, as you can see here. What we need to look at is we had initially stressed the strand in our pre-stressed bed, cast the concrete around it, and then we release the strands from the abutments or whatever's holding them. And we start losing stress in the strands. We have several different components. You see the four major components here. Elastic shortening is an instantaneous, in quotation marks, loss. It occurs over the time of the detensioning. And that is a loss that occurs because the strands are bonded to the concrete. As you transfer the force into the concrete's going to shorten while the strand is bonded to that concrete. So the strand is going to shorten, and that means you have less strain in the strand, which means you also have less stress in the strand. So that's what's going on with elastic shortening. There's a balance that occurs there between the concrete and the steel, and when equilibrium is reached, you have an effective pre-stress, less, and you have lost some stress due to elastic shortening. The rest of these values are long-term losses. They occur over time. And then also we have something that's called elastic regain. That's in the refined method for computing pre-stress losses. And that is, as you apply load back on the girder, you restrain the strand, which means you're putting a little bit of pre-stress back into the strands just due to being loaded up. That's not a real large number. I'm not going to discuss details about this any further today, but I would encourage you, if you need that kind of training or information, to look at Chapter 8 of the Bridge Manual, or take the free e-learning course that Reid is going to tell you a little bit more about later, but one of those courses is refined and approximate estimates of pre-stress loss. So you can get a lot more information there. As we move into flexural design, now that we have some of the stresses that we need, at the service limit state, we check stresses after transfer. That's going to be the highest pre-stress and the lowest concrete strength. And then we will check final stresses after all losses. So that's going to be the lowest pre-stress, but the highest strength. That will be at the 28-day compressive strength of the concrete. So that's what we do for service limit state. We also check strength limit state, check that resistance and compare it to the factored loads. We could also check the fatigue limit state, but it turns out that the specs do not require us to check fatigue for a pre-stressed girder. And the reason for that is that if you design a girder using the allowable stresses or the limiting stresses for service 1 and service 3, the stress range in the strands can't get high enough to give any problem. If you don't have well-cracked concrete, you will not get fatigue. So that's why we don't check fatigue limit state for pre-stressed design. There are stress limits for service limit state design for the strands. You see them here immediately prior to transfer. You have the 0.75 FPU, FPU being the strength of the strands, or the 270 KSI. So 75% of that is 202.5. So that's typically what we assume for our strand stress for the initial condition. Then at the service limit state, there's a limit that's given based on the yield strength. So that turns out to be 216 KSI. That rarely governs. It may govern for some additional or other types of material, but for regular pre-stressing strands, this limit is not encountered. You also see the yield stress listed here. And there is a jacking stress that is permitted. It used to be in the design specifications, but years ago, which I was part of, we were able to move that out of the design specs because people were using that number to design, and that's not its intent. It's intended to allow the fabricator to use a little bit higher stress in the strands in order to counteract some early losses due to thermal and anchor set and things like that. That is, again, in the LRFD construction specs. We have concrete limiting stresses that are, quote, before losses and then, quote, after losses. That's the way they're specified in the LRFD specs. And before losses means immediately after transfer and elastic shortening. So it's not before all losses, it's just before losses, time-dependent losses have occurred. And then after losses is the final condition, all losses have occurred, and you're up to 28-day compression stresses. I think you're probably familiar with how to compute stresses in concrete. You're just using basic material science relationships, which you can see here. The stress in the concrete is equal to the summation of the P over A, the pre-stress effect, and then the moment due to the pre-stress, and then any moments that are applied to the cross section. So that's what we're doing when we compute stresses in pre-stress. There are stress limits for the concrete in pre-stress. We have a compression limit. This is before losses or immediately after transfer and after the elastic shortening. So compression is allowed to go up to 65% of that initial specified compressive strength. It used to be 0.6. It was changed in the 2016 interims, but now it's 0.65. Then for tension, we have two limits that are given, one for no bonded reinforcement, and then there's a second one for bonded reinforcement. This no bonded reinforcement, this would be at the top of the beam where there's a tension zone at release. We're given this limit here times the square root of the strength, or less than or equal to 200 PSI or 0.2 KSI. And this limit is going to control for most of our concrete strengths. So it'll be capped at 200 PSI. If you are allowed to use this value down here, which is essentially the modulus of rupture of the concrete, you will then have to be supplying reinforcement that uses a working stress of 30 KSI for grade 60 steel, as you can see down here. Half of the yield stress. So this is just a graphic that shows you for a girder, you'll end up with some tension at the top. You compute the area of that tension. Essentially, you're integrating it, but we're just making it simple here, neglecting these little triangles. So you simply compute the tension force, and then you take the tension force and divide it by the working stress, and you get an area of steel that would be required to be placed within that tension region in order to use this higher concrete stress at release. Now at service limit state, after all losses, so this is years from now, there are limits on compression, two limits, one due to permanent loads and then one permanent plus transient. In other words, if your live loads are on it, you would have this limit. That's for compression. And then for tension, you have two different limits, 0.19, which is equivalent to 6 square root F prime C if it's in PSI. So 0.19 for the general case. For severe corrosion, it comes down to half of that. And then some of DOTs use limits that vary from this. In fact, there are a couple of states that use zero tension. That can have ramifications in a lot of ways, since there's more pre-stress being introduced than is really necessary. So we check our stresses at transfer. Once the strand pattern has been established, we take a look at transfer. The critical location may be at the hold down for a draped strand. The ends of the girders, however, is where we typically have issues, because at the end of the beam, we have low self-weight due to the girder and low moment due to the girder weight to counteract to that pre-stress moment. So you simply don't have enough weight or moment from the girder to counteract the pre-stress. Therefore, you may have too much compression or tension in the girders at the end. So debonding or draping are two of the main methods used to control these stresses. We'll get to that after a little while. So typically we just talked about checking the stress. Now we're at service limit state. Now we're checking the strength limit state. You compute the factored moments as we normally do. You compute the nominal flexural resistance and what can that cross section resist at ultimate. That gives us the M sub N. We factor that and compare it to M sub U. And then we can also used to check maximum reinforcement, and then there are minimum reinforcement requirements, and I'll go into those briefly. Strength limit state for a girder typically doesn't govern design when you have composite girders. It's more likely to govern for shallow members like voided slabs or box beams, but we still have to check it. There are two approaches for computing the nominal flexural resistance, M sub N. One's the approximate method. It's given in the specifications. It's a simple approach, closed form solution. It's very direct, easy to do, often used by computer programs since most of us aren't doing hand calcs anymore. And then there's the other approach, which is using strain compatibility, which is more detailed. It's a general approach. You can apply it to any shape, any material. So it's applicable to essentially all design cases. It is iterative, however, and has a lot of calculations involved and actually uses stress strain relationships for the concrete and the strand. If you're looking at the approximate method, we'll discuss that briefly. There are equations given, and really the main issue that I did touch on with about one slide, I think it was in the first session, that is checking the capacity of a pre-stressed girder is essentially the same as checking it for a reinforced concrete girder, except we don't know what the steel stress is because we don't have a yield plateau. So there is a method for getting to that FPS value, but otherwise it's the same as reinforced concrete. Here is the equation for that FPS value. Very simple equation, and it does have one quantity here, the constant K, which is the same. It's fixed based on the definition of yield. So for low relaxation strands where the yield stress is 9/10 of the ultimate, K is always going to be 0.28. So this equation becomes very simple to compute. The conditions at nominal flexural resistance are, as I was saying, the same look as what you would use for reinforced concrete, except for one important item. There is the initial stress in the strand or strain in the strand that has to be considered, epsilon P0. It appears in some of the shear calculations. But what this is, that's the pre-strain. You've pre-stressed, it's the strain that corresponds to the pre-stress in the steel. So you've pulled the strands and then you cast concrete around them. Well, there's a locked in difference in strain between what's in the strand and what's in the concrete. When you cast it, there's a high strain in the strand and no strain in the concrete, and then they bond together and that strain is always going to be there. So that's what this is. So while you can compute strains in the concrete or in the cracked concrete, essentially for reinforced here, you can compute this strain from your C over D ratio, but then you have to add to it this strain for that initial pre-stress. There used to be a maximum reinforcement limit, a reinforcement index. Now that is all taken care of with the transition concept for the phi factor, the resistance factor that was introduced in 2005. This is the figure that comes out of the LRFD specs. And we simply transition the phi factor for pre-stressed girders here, the solid line. There's an an equation that gives you that variation from having a phi factor of 1 at a strain of 0.005 down to a phi factor of 0.75, which is the compression phi factor at a strain of 0.002. And that would be the strain in the concrete at the level of the steel. So that's how we now deal with maximum reinforcement. Minimum reinforcement, we compare the flexural resistance now to these two limits. 4/3 of M sub U. So you have to have a significant overstrength compared to the factored loads, or you also need to have a resistance, factored resistance, that is greater than the cracking moment. Cracking moment's based on the modulus of rupture, but it also includes a number of other factors. It's a pretty long equation. I don't have it repeated here. And this limit used to be M sub R just had to be greater than 1.2 M cracking, but now it's an equation that's probably less than 1.2. But what we're trying to do there is you don't want the beam to crack and then fail. We have to have some ductility in the system so that there can be some additional cracking and deflection and that sort of thing prior to a failure occurring. So this is how we set that. One thing to note, I'll just bring this to your attention, is that both the maximum and minimum reinforcement concepts, the ideas of ductility, can present some problems when we're looking at new reinforcing materials such as stainless steel or carbon fiber, or even for UHPC. There are just some different approaches that are needed. Because for the strands, for example, you don't really have the yielding and the ductility of the material that we typically have had. So there's some discussion about that ongoing right now. T10 is considering that as they're considering these new materials, T10 being the AASHTO committee that writes our chapter on concrete design in the LRFD. And there's also a series of Aspire articles where we are addressing that right now. We'll just touch on the strain compatibility approach that can be used for these other types of materials. It simply uses the stress strain relationships. It's a straightforward concept. I would encourage you to look it up somewhere. There are a couple of slides here that I've hidden that are in the presentation that you can look at. It'll give you a little bit more information, but it's a very general approach that can be used for any material. And sometimes the design programs will allow you to use that as well. So that brings us to the end of the first part of our design section. It's not the total one yet because I have a 1B that will follow here. So we'll move on to that. And somehow I didn't get all my, Sorry about this. I was very careful to get everything all lined up, and then apparently I reviewed my slides again. So we're now going to go into a discussion of draping and debonding. That's a typical discussion. Some states and pre-stressors like one way or another, either draping or debonding. Others want the other way of doing things, but really they're both addressing the same issue. So as we were talking about design, flexural design, we compute a number of strands at midspan. Typically, it's going to be defined by service. It could be defined by strength. For girders, it's almost always by service. And if you were to look at the stresses along the length of a beam at the final condition, you can see that here we have the compression stress limit, the tension stress limit, and we're just satisfying this tensile stress limit. We're not too far from the compression, but this is typical of what we've done. So we figure out what we need for moment capacity or stress limits at service. And that's how we define the number of strands that we're going to have. And this is taken from output from PS Beam by Ericsson Technologies. We then take a look at the stresses at transfer. So as I mentioned earlier, when you're at transfer and you move to the ends of the beams, you don't have the dead load to counteract. And this is what that same girder will look like if you take a look at it at transfer, and you see that we have exceeded tensile stresses at the top, and we have exceeded compressive stresses at the bottom. So we have to, that is if you're just taking a look at the exact same design, you've done nothing, they're all straight strands, they're all bonded all the way to the end. This is what it would look like. So we have to have some approach to deal with those stresses. There are typically about 6 methods that we can use. The first 2 are the main ones that we've talked about already a few times, and that is draping and debonding. We can also add some top strands, and we can also add some strands within the more central portions of the girder. And those are the ones that I'm going to be talking about today. There's also a couple of others. One is adding some mild reinforcement at the end to allow that higher allowable tensile stress. I'm not going to talk about that further. We've already discussed it adequately, I think. And then the other is increasing the compressive strength at release of the FPCI. That's not really effective if the tensile strength governs, and it's not at all effective if the 0.2 KSI tensile stress is governing. It could be useful if the compressive strength were governing at the ends of the beams, but that's probably not what's going to be happening. So while it exists, this method is something that we'll neglect. So we'll move right on in to a discussion of draping, which can also be called harping or deflecting. We'll be calling it draping. When we drape strands, we are reducing the concrete stresses at the ends by reducing the eccentricity of the strands. So when we reduce the eccentricity of the strands, we reduce the pre-stress moment. But the force is maintained. All of the strands typically are bonded to the end of the beam, so we have the full pre-stress force, effective pre-stress, other than at transfer at the very ends. That's available for the full length of the beam. So we're changing the moment only. So how do we do that? We raise the strands in the web until the stress limits are satisfied at the ends. That only works for the strands in the web, because they have to be able to be raised up. If out in the flanges, there's nowhere for the strands to go. All strands are active for the full length of the girder, and the pre-stress force has to resist that hold down force. Because those strands are being draped, they're being deflected. So there has to be a way for that bed to resist that force. The shear resistance, it turns out, is also improved using this method because you have an inclined pre-stress force that acts in the direction that resists shear. That's not a large force, but it exists. And also the full pre-stress force is available for the full length of the beam. So V sub C is improved by having that pre-stress force available. So here are a couple of little figures to try to convey what's going on with draping. If you had straight strands, this is what you would get. The top diagram is showing us the force. The bottom diagram is showing us the moment along the beam. And in this case, they're identical. The strands are straight, the force is the same, the eccentricity is constant. So the shape of the force diagram is the same as the shape of the moment diagram. However, you're going to end up with excessive stresses. Now, I do show some slope at both ends of this. That's due to the transfer length, as it's indicated here. So this is just a schematic. It'd be a very short beam in order to have a schematic that looks like this. When we drape the strands, the top diagram remains the same because we still have a constant force for the length of the beam. However, the moment caused by the pre-stressed effect does change. You see how this is reducing. This would be the hold down point where the strands are held down, and then they start moving up through the cross section. So the eccentricity of the group of strands is reduced. And that's how we get into the range to get acceptable stresses. So that's the difference between the straight strand design and a draped strand design. It turns out that using draped strands can allow us to reduce the release strength in some cases. So that's a benefit. Typically, we use 2 hold downs, one on each side of the center line of the beam. And it's recommended that a fixed distance be used. That is for the producers. Down in my neck of the woods, down here in North Carolina, and in South Carolina does the same. Both of those DOTs use a hold down point that is 5 feet on each side of center line. And that stays the same for all girders. It works well. I would recommend that you avoid using a ratio of the girder length to locate the hold down. That's the default in some design programs, but that means that if the producers are going to make girders using those numbers, they have to keep moving that hold down point around for every girder they make, or every group of girders they make. And that means they're burning holes through their forms and repairing them. It's not a terrible problem, but it's just an efficiency that can be had that we as designers can contribute to the process. The hardware also can only be positioned in certain locations. These hold downs have to be tied down to the bottom of the bed, and you can see these blocks. Those are keyed into a bar that's running along under here to counteract the force that is acting upward on this hold down. So they're going to have to move the hold down point anyway. You could use a single hold down potentially. There are some states that allow that or encourage it. One thing to note though is that the force that's being generated on a hold down is by the angle change. And if you have a single hold down, you have an angle change on both sides of that hold down, which means you have twice the hold down force. So you can exceed the capacity of the hold down faster for a single point hold down than for a 2 point. Usually we see 2 points. We as designers typically design just showing one hold down on each side of center line. The fabricators may have to move those around again because they have hardware that they're tying into. So the shop drawings may show split hold downs, not only because they have to move them because of the locations, but also there are capacities involved with these hold downs. We as designers don't really need to worry about this. It turns out that moving the hold downs around a little bit or splitting them apart, as you see here, has a very, very minimal effect on the design. So we don't really need to worry about that. The hold downs are limited in strength by the capacity of the hold down device and the rod that is tying it down to the rail down below. And also the rollers have limitations as well. So the load on the hold down is affected by the number and the slope of the strands. So having your hold downs closer to midspan will reduce the slope. For draping strands, safety is a concern. There are different ways that you can get the strands into these draped positions, but you're having to hold them up or push them down or whatever it might be. Typically, we see tension, at least in our region, that you tension the strands and then you lift them up to the draped position. That's what's going on with this device here. This is simply one of the types of strand holdups, and the strands start down low, and then you would raise this up to get them in the top position. And then there's a pin that goes through the bar that's attached to all this. That pin has to be put in. A crane would grab onto this to lift it, and then the pin has to be put in to hold that strand in the strands in the right position. So that can have some significant safety concerns. So stressing them in the draped position would be preferred. If you're going to drape them, it's better to drape them in that, or to stress them as they are already draped. That way you're not having to move things. Some states allow that, some states don't. There is a standardized procedure that's given in the PCI manual. So this is something that's commonly done to stress them through hold downs. They are low friction hold downs or hold ups. So those are something that can be done. One thing to note about strands is that raising the strands is going to provide additional elongation. You're taking them from a straight position to a deflected position, so that's a longer distance. So the strands are being stretched, so they're increasing the stresses in the strands. Therefore, the draped strands are tensioned to a lower stress than the straight strands. So that's something that has to be considered. Also, if you're draping strands in the final position, so you're pulling them through all of the deflection points, the draped strands are going to, again, be a slightly longer than the straight strands. So the elongations are going to be different. So in both cases, draping adds complexity to the stressing operations simply because you have some different forces and elongations. So it just adds a little something else to the fabrication. It also takes a little bit more labor in order to install draped strands because you have to feed them through the rollers and all that sort of thing. And strands, while you think about it, it's just a strand. So what? But like I have here, 500 feet of 6/10 strand weighs about 370 pounds. And you can see it's not one guy carrying this thing down the bed. That's one strand they're carrying, but they're having to pull it down a long bed. So typically it takes a good bit of labor to do this. You can see here, I think these guys, I don't know if they're acting on different strands or not, but they're having to work pretty hard to drag that strand. A sled can be used if they're wanting to drag several straight strands down the bed at the same time. So that's the discussion about draping. Now we're going to start talking about debonding. That's the second approach to controlling stresses at the ends of the beam. What happens when we debond? Just the name of it, we're debonding a strand. So we are not allowing it to bond. So what we're doing is we're reducing the effective pre-stress force at the ends of the beams. That's because we are reducing the number of strands that are bonded at different locations along the girder. So when we do that, we're reducing the force, but since it's tied to the moment, we will also be reducing the moment. But the main effect is we're reducing the force and then the moment is coming with it. So the bond of the concrete is prevented for a specified length at each end of the girder. That means that the force in that strand is not transferred to the concrete. And the debonding has to go all the way to the end of the beam. You can see here the debonding is actually sticking out. It's still around these 10 strands, 5 on each side. The strand has to be able to suck in, and it has to be able to not, it has to be able to detension itself. It has to not be debonded to the concrete. So it has to be able to slide in order for that force to disappear in that girder, in that strand, up to the point at which it then becomes bonded and the force begins to pick up again. Debonding is almost always preferred by pre-stressors. I know of one plant years ago that I used to know guys there, and they were excited about draping. They said that's what they wanted. But I think everybody else that I've talked to since always says they want debonding because it's safer, it eliminates cost of the hold downs. And in this case, I mean, there is a cost that's associated with installing the debonding, but it's not as significant as these others. Typically, a debonded design is also going to require a few more strands than a drape design, usually in the neighborhood of 6 strands. So here's some similar schematics to what we had for draping. And we'll look at a schematic about the effect of debonding, where we have some strands, the number 1 strands, are bonded all the way to the end. The number 2 group of strands are bonded with a short debonding length, and then the number 3 group of strands has a longer debonding. So now we'll take a look at what we see down here, and the force and the moment diagrams are the same because the force is changing. There's a little bit of difference with the eccentricity, but typically you debond and try to maintain about the same eccentricity. So we're neglecting the change in eccentricity for this example. You also see that there are still transfer lengths, sloped lines at each of these. So if we look at the first group of strands, you can see here that these are bonded all the way to the end. So the transfer length starts at the end of the girder and then it comes along. That's the first group. The second group of strands begins to contribute to stresses in the cross section at the end of the debonding. So then you have a transfer length, and then you have the effective stress available in that group of strands. And then finally, the third group of strands are stressed. They start picking up or contributing stress into the concrete at the end of the debonding. Then there's the transfer length, and then you get an effective stress for those. So in this case, this diagram applies, as I say, to both force and moment. And there you can see that the moment has been reduced at the ends due to the change in the force. As I said earlier, for debonding to be effective, the bond has to be prevented all the way to the end of the girder so that that strand can become detensioned. And we want to make sure that the concrete doesn't encounter that strand in the debonding length. In order to do that, we have to make sure that the ends and anywhere along the length of the sheath has to be sealed to prevent entry of concrete into that girder or into that strand debonding material. Here's some examples. There's a 2-piece snap together sleeve. It comes in certain lengths, but you can snap these 2 pieces together and it gives a good tight fit around the strands. You can also use a solid tube, but in that case, you have to thread the strand through the tube as it's being placed in the bed. There's another method that's a split sleeve, but you have to tape those along the length, and they're generally not allowed, but they may be allowed and can be effective if properly used. So you have to access those strands wherever they may be in the cross section. You have to access them and apply this debonding to the strand and then be able to get in there and seal it up as well. Well, what's the effect of debonding on design as we compare it to draping? The shear resistance is reduced. Well, of course, it's assumed, yeah, it's changing the stresses. So we've got that taken care of. But here we're saying that the shear resistance is indeed reduced because you have a reduced pre-stress force at high shear locations at the ends of the beams. You also have no vertical component of the inclined pre-stress force that you have for draping. But these can be addressed by adding stirrups if necessary. So you simply consider this in your design and then you design accordingly. Something else that we have to check in our designs is longitudinal reinforcement, and that capacity is also reduced. So that's something that we have to be sure that we take a look at and consider. You can address that by adding stirrups, or you can address it by adding longitudinal reinforcement, but this really isn't the greatest idea because stuffing additional rebar in around the strands can really increase congestion and make it difficult to get the concrete in. The camber's affected in this case, and we simply have to consider these effects as a designer and deal with it. There are debonding limits that have been established. In fact, they've been revised in recent years. June of 2019, so almost 2 years ago, AASHTO approved the change in debonding requirements. Here you can see sort of a summary of the requirements. And one of the significant issues is that there is no longer a total limit, a total number of debonded strand limit. It used to be, as you see there, struck out that we couldn't exceed 25% of the total number of strands debonded. But that is gone. There is no longer a total number of strand limit. There are limits on numbers in a row and some other things, and I will quickly go over those. You can review these slides later if you want some more detail, or just take a look at the specs. So probably the most significant thing that we have to remember is that you only get to debond 45% of the strands in a row. So again, there's no total limit, and this will affect the limits, and you'll see some examples. I have two examples in a few minutes. We don't want to terminate the debonding of more than 6 strands at any location, or if you have fewer, maybe it'll be 4. But that's really intended to reduce any potential for cracking at the end of a bunch of strands being, the debonding being terminated. There's also a longitudinal spacing requirement for the debonding termination locations. They need to be at least 60 dB apart for a 6/10 strand, which is what we use typically nowadays. That's 36 inches, 3 feet. Again, we're avoiding stress concentrations. And then we want them to be symmetrical. Everything we want to do typically needs to be symmetrical so you don't get sweep or any other issues. So they're symmetrical longitudinally as well as across the cross section. It does say in the specs that you are to alternate bonded and debonded strand locations. That doesn't mean that you have to have alternating, but what it means is if you have debonded strands, they can't be surrounded or next to other debonded strands. I came up with some additional wording that seemed to work better for me, but debonded strands shall not be located adjacent to other debonded strands. This seems to say you have to alternate no matter what, but you don't always debond. So you just simply don't want debonded strands next to each other, either horizontally or vertically. You'll see some examples again later. There is a provision that's been in here in the specs actually for years that says you modify the development length of a debonded strand, typically using a multiplier of 2. This isn't any change, any different from what it used to be. For simple span prestressed girders, there's some other maximum lengths that have been given for maximum lengths of debonding. Typically, we don't see that enter in. You simply limit the debonding to what it needs to be. You don't just keep adding it for some reason. So I'm not sure how much of an effect this is going to have on things. It also says if you're using, the next item is related to continuous for live load girders. And it essentially is saying, consider all the effects on the design. That's basically what that's up about. Then there's something that's sort of interesting for single web flange sections. In other words, I-beams, bulb tees, all that sort of thing. You need to bond all the strands within the horizontal limits of the web if you have either of 2 conditions. Either you have 25%, more than 25% of your strands are debonded, or if the ratio of your bottom flange width to your web width exceeds 4. In either case, if those are satisfied, you must bond all the strands in the web. We'll see that in the example in just a minute. You also need to bond the outermost strands, but only in rows that have the full width of the flange. So as you start moving into rows that are narrower than the full width of the flange, you can debond those outermost strands. And you typically want to put your debonded strands farther from the center line if possible. Here's an example for a multi-web, in other words, a tub type girder. We have a similar requirement to the one I just talked about, where you have to bond these strands that are in a width of the web that's projected upward. So these strands would have to be bonded if you meet those requirements that were in the previous slide. Otherwise, for other sections, you simply try to distribute your debonding accordingly, uniformly in the cross section. Here's one example. This is actually in the commentary to the LRFD. This is a PCI bulb T section. So you see all the requirements that apply here are indicated. So these strands here are the outermost in the full width cross section part of the girder, so they must be bonded. Then you see two different patterns. On one side of the center line, I have red strands debonded. On the other side, I am debonding orange strands. You end up with the same number. They're both 6 on each side, but you can see that there are different numbers of strands. They all agree with, although looking at this one, you would have 50% and you're not allowed 50% in a row. But this is coming out of the, at any rate, we'll move on. Do what I say, not what I have shown here. I guess really this one shouldn't have 12 strands. This should be limited to 10. So you need to check those two requirements, whether the flange and the web width ratio is greater than 4, which it is. So that means the center strands have to be bonded. Also, we're debonding greater than 25%. So again, both conditions are met. So we must bond all of these within the width of the web. Now, these strands here are right underneath the edges of that flange, but this is an example out of the LRFD, and they seem to think that those then do not have to be bonded. You can also see here how we have moved the strands around so that they are alternating. They are not next to other debonded strands. Here's an example that I received from Will Potter at Florida DOT, who was working very hard on setting up all this wording in the specs. This is simply an example for a Florida I-beam. Same set of requirements. I'll let you take a look at that. In this case, I do note that we're 45% or less strands. This one's right at it, where you had 4 out of 9 strands were debonded. So here we're getting up to 37% of the strands are debonded, or in this case, 34% if you have all the strands there. So we're much higher than the 25% than what it used to be. As far as debonding considerations, we should, as designers, think about selecting locations, although fabricators can adjust strand locations in the shop drawings. All the debonded strands typically are sealed after they are cut, after they're removed from the bed, cut off flush, and then sealed. One thing that's nice about debonded strands is it does eliminate any conflicts for those strands passing through regions where you may have holes for bolts or rebar or whatever. So what do? You drape or you debond, and it's really recommended to try to use straight strands first, then go to debonding. And if the debonded design requires more than 6, as is what we do in North Carolina, for example, then you might go with the drape design. But one thing to note also is you can combine draping and debonding. There's nothing that says you can't. No reason physically that you can't. I've had a little too much fun here, so I'm going to have to start moving quickly through these. Been giving you all too many extra details. We do occasionally add top strands. They will improve the stress conditions at the ends of a beam. I always thought for years that if you add top strands, then you're essentially eliminating bottom strands or counteracting them. So you're going to have to add some more bottom strands. It's not quite that simple, because we have to remember that every time we put a strand in, we're not just adding the moment part, but we also have a P over A. So you are adding pre-compression when you add those top strands. You can also use temporary top strands. There is an article that appeared in Aspire that talks about adding top strands. I won't spend much time on that, but he did add the top strands here. There were 4 strands that were added. It only changed the stress on the bottom at service by about 110 PSI. So it wasn't a significant change. And I'll talk about this next item, the kern point, in just a moment. The specs do have temporary top strands that are discussed. Temporary top strands are added in the top of the girder, but they are de-bonded in the center part of the beam. So here they're bonded at the ends and then de-bonded within the center portion. But the one caveat is that you have to detension that strand. Just because it's debonded, there's still a force there. It's because it's debonded doesn't mean that it's disabled. It has to be able to detension. So you have to provide an access port that you go in and you actually detension that top strand. And then in this case, you have top strands that are improving conditions at the end, but then they've been eliminated from affecting the conditions out in the rest of the girder. So that's an important thing to think about. It is in the specs, as you saw. Typically, we detension those strands after erection because they help out with lateral stability during handling an erection. You do need some notes and such. The contractor needs to understand what's going. You can use post-tension details. This is from WashDOT. They have both pre-tension and post-tension top strand details. As I mentioned, you have to provide those access ports. The single port should be near mid-span, and I just have a picture here of a project years ago where they thought this was a neat idea, but they put ports at both ends. Well, somebody's going to burn their strand before the guy at the other end is going to burn his strand. So that didn't quite work out well for them. And the size of the port has to be big enough so that you can play the flame back and forth, and you actually detension those strands just like you would by flame detention that we talked about the other day. One issue with this is that if there's a potential for water to get into these, and if it could freeze, you can split the concrete along the detensioning. So you need to protect these access ports to keep water out. You really need to help the contractor to understand that you aren't cutting the strands. You're not having a race to see how fast you can cut them, because that means you would have more energy release. Instead, you want to debond them. Not debond, but detension them, just using the same procedures you'd use in the plant to detension strands. You can add some strands in mid-height. The concept of the kern is explained here. It shows up better. Let me show here. If you apply a strand at the top kern point, it applies no change in stress at the bottom. So anywhere that you apply force between those add strands, between the kern point, there's the top kern point, there's the bottom kern point. Anywhere in here, it's not going to create any tension on the opposite side. So that's a useful concept to be aware of. Design programs like here from PS Beam, it does locate the kern points for you. It's easy to compute. They were shown on an earlier slide. Here's an example, a 52 strand design with 12 draped strands. And I look at that. This is the way it looked with the draped strands. And then you want to say, okay, I want to develop a straight strand design. Can I do it? Well, if you just take the 50 strands, you have overstresses. And then there are a bunch of slides here that I've hidden so you can actually see how I've stepped through it. But here I've added 4 top strands and then 2 within the kern points here in the middle. So that made the design work. but I had to add 6 strands compared to the draped design. So you can also evaluate girder stresses when lifted, and that kicks some additional issues into your design. And let's see, there are a couple of other issues here. I am going to skip these right now, but if you would like to go back and check these 6 slides or so that I'm going to skip, you can get the additional information that we have there. So we will now move on to the beginning here of section 2, which is about camber. And I have about 15 minutes to go over this. So we'll talk about some girder sections and then some camber. Give you a little bit of a history lesson on some of what's going on. First, standard girder sections were developed in the 50s. There were some AASHTO PCI sections, the types 1 through 6. Bulb T girders came later. Then it was pretty stable for a while, and then states started developing their own shapes again. In the 90s, some new shapes were developed so that you could get a larger bottom flange in order to allow more strands to give us longer spans, and wider top flanges to improve stability. So the PCI Northeast at the time developed or I guess it was PCI New England at the time, developed a regional standard. And then the Mid-Atlantic states took that and modified it. So here you can see the article about the PCI New England Bulb T, a couple of pictures pulled out of it. And this was developed back when we were thinking metric. We thought that was going to happen. It has curves. It doesn't have square corners except down here at the bottom where we have a chamfer. There were design curves that were provided. There were charts. There's some people that you might know that with pictures taken back in the 90s. So then the PCEF folks, the Mid-Atlantic PCEF, Precast Concrete Economical Fabrication Committee is what that PCEF stands for. They said, well, we want to come up with some interchangeable sections to the PCI New England. But one of the people working on that said, I don't want any curves. I want people to be able to cut straight lines when they're doing formwork for diaphragms. So that's why there aren't any curves. So it was intended to be equivalent. It was intended, we laid it out. I was actually involved with this. We tried our best to get the section properties to be similar. You can see some comparison tables here that I pulled out of some numbers that I found from 1999. Some of the section properties are a little different from what shows up in the New York State DOT standard drawings. But the differences between the Bulb T and the PCEF sections are small for these section properties, generally maybe 1 to 2% difference. So they are essentially interchangeable. Part of the difference is simply due to the metric conversion. One of the things we did with the PCEF girders is that we got real excited and we came up with all these different combinations of different flange widths, different web widths, different bottom flange depths. So all these sorts of things, and of course, different girder depths. So we ended up with a family of 162 shapes, which that's probably a little more than we should have. But that's what we came up with. And so some of the DOTs have adopted a limited number of those sections. Here are 2 examples, the New York State and the VDOT, showing essentially the same cross sections. With one difference, a major difference that shows up is that the VDOT section only has a 7-inch tall bottom flange, where the New York State DOT is using the 9-inch. Turns out that unless you're really stretching a girder, you can get away with a 7-inch for almost all the designs. And it's only when you really push it that you need to go to the 9-inch bottom flange. But, you know, the section's there and it works. The New England bulb T also has a 9-inch bottom flange, essentially. Standardization between girders, between DOTs would be very nice. There are differences, however. Here we can see that some of the reinforcement details, like in this case, the distance to the bottom of the row of the strands differ. Here's the VDOT, which is a PCEF section. The New England bulb T, I don't know if you can read it. Next time I do this, I'll put some details in here. I think this is 2 3/4. See if I can read it on my other screen here. Yeah, I think that's 2.78 inches, and this one's 2 1/4 inches. Many states just use 2 inches to the bottom row. So that would be nice to be constant, but as we saw in pictures a week ago, those strand patterns can be adjusted for different states. So it's not the end of the world if one does have to move them, but it would be nice to have them consistent. Stirrup details can be different. The confinement bar details can differ. So here's just some a couple of details from the New England bulb T and the VDOT sections. There are other standard bridge sections that can be used. You see over down the right side of the screen, the New England bulb Ts, of which there are 3 different varieties. The New England decked bulb T is another section here, and then full depth precast decks. New England or Northeast, PCI Northeast has been very active over the years in developing standards and sections. They've really taken a leadership role in that. So you can see on the website all of these details and information about these cross sections. So it's been very helpful to have that information available, and other parts of the country are using them as well, especially the next beams. And with that, we will get into some camber discussion. Camber is always a point of discussion, it seems, when talking about pre-stressed beams. And one of the most important things that we need to realize when we're talking about camber is that those numbers are estimated. And they are estimated with a bunch of variables, some of which we have control over and some that we don't. There are different approaches to estimating cambers. There's the multiplier method, there's improved multipliers, there's detailed methods. The PCI bridge design manual goes into a discussion of some of these things, but a lot of factors affect the cambers. And I think I actually have shown them here. The pre-stressed force, the pattern, how you did it, whether it's draped or debonding, and then geometry. All of these things can be pretty well known and can be controlled. So those factors are easy to handle. But then you end up with factors like this with the material properties. Yes, the release strength is probably going to be pretty close because they're monitoring that to cut the girders down. But the modulus of elasticity has a considerable scatter in any case. I mean, that's just concrete. The weight of the concrete will vary. Oftentimes we assume 150 pounds a cubic foot for the density of the concrete with reinforcement, and it can be significantly higher than that if we have a lot of strand and rebar in it. Pre-stress losses are going to have variation. So as you get all these variables in there, it starts affecting those cambers. Also, you have age at pre-stress, age at erection, and these affect the modulus and things. You also have environmental conditions, and many of these things we don't really have any control over. The multiplier method's the easiest. It was published in the PCI journal in 1977 by Les Martin in an article, and I've talked to him, and it was just sort of a back of the napkin kind of thing. It wasn't based on a whole bunch of research. It was just a reasonable approach to get an estimate of cambers. They're very straightforward calculations, and all you do is you apply multipliers to each component of the elastic deflection to predict long-term behavior. So you have an uplift force from the pre-stress and then all the deflections due to self-weight. So we have some assumptions as far as what we look at for the initial cambers. We use the initial values of concrete strength and pre-stress and modulus of elasticity. And then for any of the later components that we compute, we would use the 28-day strength and the modulus at 28 days. So we're assuming that the girder remains uncracked at all load stages, and we transform the deck and do all those sorts of things. Here you're looking at the initial camber, and what we end up with is that we have the release, the pre-stress effect is going upward at release, the weight of the girder is going down, so you have a difference between two quantities, and any variation in either quantity when you have a difference can make a significant difference in the total. So it's something to be aware of, that that's why we have so much variation in camber, one of the factors. So you see here, there's also some other equations that I've skipped here. They're hidden in the presentation. The final deflection of the structure, you use the pre-stress upwards, the girder downward, and then you add any subsequent dead loads. These factors are affected by creep and shrinkage and all sorts of things like that, temperatures. Here are the actual multipliers for a pre-stress element with a composite deck. You have a group of multipliers at erection, and then a group of multipliers at final. You also can get multipliers for sections without a composite deck. These multipliers up here at the top are the same. There's no effect, whether it's composite or not, that at erection it's unaffected. But here, just for comparison, you can see the difference in values between the composite and the non-composite. Because with the non-composite, you don't have additional major load that's being applied. And also the composite section, since you've changed the section properties, it tends to freeze the camber that's in the girder, and it doesn't change as much as we would anticipate. So to compute using the cambers, or compute the cambers using the multipliers at release, it's simply the values of the deflections. At erection, you apply the multipliers, and then you add dead loads, and then you would add these two numbers together to get the final. And this is neglecting any of the multipliers. This would be for a composite section. So you don't put any other multipliers on these added dead loads like the table that we saw earlier would tell you to do. One thing I want to go through very quickly in my last minute here is that we have to be careful how we use our buildups, use the cambers, because typically we have a minimum specified buildup. We use that to set the buildup at the bearings, but we have to consider cross slope and camber. The contractor needs to go through and measure the actual girder elevations once they get erected. But I would encourage you to think through these slides. When you have cross slope, which you always will to some degree, but especially if you have curvature, your minimum buildup isn't defined at the center of the beam, it's defined at the edge of the beam, because especially with our wider top flanges, that can be, that's a 1/4 inch a foot, that's 1/2 inch difference. So this is where the minimum occurs. And if you have a curvature, the girder is thrown inside the curve, so you have a further reduction in the minimum buildup due to the curve effect. So we need to remember that. Also, the sun affects camber. So if you are measuring camber in the yard after it's erected, whatever, you need to do it early in the day. Bearing locations make a big difference. And then I have a couple of summary slides. I'm going to skip over those because I'm at the end of my time. But that gives us information on girder sections as well as on cambers. And I would encourage you to take a look at those. And certainly if you ever have questions, you simply need to talk to your pre-stressor, talk to your local neighborhood fabricator and ask them questions. With that, I'm going to pass this over to Greg Gorman, and he is going to give you some exciting slides on accelerated bridge construction. So I'll let you take it from here, Greg.
Okay, thanks, Reid. Okay. All right. Hopefully that's sharing okay. You see my screen?
Yes.
Okay.
Looks
Good.
good.
All right. Well, thanks, Reid. I get to talk about one of my favorite subjects today, and that is accelerated bridge construction, or precast, prestressed concrete accelerated bridge construction. And just to say that this session is normally a standalone. We've incorporated it into the design seminar, but we've done this presentation many times in many offices. And so all that to say, if you're interested, we can do the seminar or this presentation rather in your office, either physically or virtually. Just get a hold of Dawn or Rita as well. I mean, we haven't done it in the Northeast. The Northeast, I would have to say, Northeast states are maybe a little bit farther ahead on accelerated bridge construction, and but I certainly offer it there. And I either read an article or possibly saw another presentation where I believe the state of Vermont actually, in their project planning for all of their bridge structures, one of their early decision boxes is, can we use accelerated bridge construction? So anyway, with that, I'm going to move on to the presentation. And let me There we go. Okay, first point is it's not a new concept. Making pieces off site and bringing them on site and install them is not a new concept. It's kind of a new delivery system, non-conventional way of building a bridge structure for us, but it's certainly not a new concept. We're going to look at 4 example project types, and these are 4 that we've done. We've done different varieties of each, and there's been others. We're certainly not the gatekeeper of all great ideas in total precast, but we're going to look at least 4 different ones this morning, or this afternoon now. Starting with the top left, we'll look at the PennDOT standards detail. This is a bridge over I-78 in Lehigh County. And going clockwise, we'll look at what we call a modular deck. The project we'll be looking at is the Wampum Run project in Lawrence County, Pennsylvania. And then going down to the bottom left is what we call an abutment block. This type of delivery system kind of came out of District 9, PennDOT in Pennsylvania, and has mostly been used there. And that's the Sherman Run or Sherman Valley Run Bridge in Bedford County. And then the final one, and not necessarily in the order they're presented here, but the last one we'll be looking at is a cast in place component replacement, or also known as emulative design. And we'll be looking at the project. It's the Ashcombe Bridge in Bedford County also. Okay, as some of you may have been online last week when I did the virtual tour, and kind of started with, it all starts with the engineering, and kind of the same way here, and especially here because there's a lot of parts and pieces that need to fit up, really well. So we've been doing 3D BIM with Tekla Systems by Trimble for some time now. A question was asked after the first, after last week's session, whether or not all of the models that were presented in the presentation were done by the fabricator. And the answer is yes. And all the models and 3D drawings and things that you'll see in the presentation today are the same. They were all created, by us in-house. But the advantages, a lot of advantages to 3D BIM. Some of the advantages in a complicated project like this, there's about 154 pieces of precast. And this job, you see, I can determine pretty quickly with the information in the BIM model that there's north of 180,000 pieces of reinforcing and hardware and stuff in the skeleton of this project, from footings to walls to columns and beams, deck slabs, and all of the above. Another advantage that we have in my first presentation, I mentioned it's always good to have a young engineer in your office. In that case, that had a drone and can get some really cool pictures. But it's also cool to have a really young engineer that has a 3D printer at home that can kind of get the idea moving that we needed to get one in the office. And so we can make 3D prints of a lot of the pieces that we make. And in this case, this is kind of a complicated abutment wall with an integral corner column. And so lots of times when we get a complicated piece like this, we'll do a 3D model, send it down to the shop with the shop drawing, so that the carpenters, when they're doing the form work for this, they're thinking inside out, very complicated. So this just kind of is another tool that helps them figure it out and put it together. Here's another example. And again, I show you this. It's not a bridge project, obviously. This is the Tower of Voices, Flight 93 Memorial. But on the right, you see the full-scale model. When I say full-scale, it's not obviously the size of the monument, but it's a large model that we spent a lot of time with in the conference room, looking at the different parts and pieces. What are the best way that we can connect this thing together? But just to show how 3D can really help with complicated geometry and pieces. The picture on the left is one of the columns. And actually, this is a column only for the mock-up. So it's a rather small column for this same project. And here we see the project fully erected. It's 93 feet tall, 15 feet in diameter. It's located near Shanksville, Pennsylvania, in the National Park for Flight 93. And just a very interesting project. But again, just to show how 3D BIM technology is can really help with complicated, low tolerance fit up type geometry, and a couple BIM models on the right as well. Okay, so we're going to start off with the abutment block type. This is a Sherman Valley Run project in Bedford County, and we'll start with the foundation. And these pieces were match cast and post tension together. This is the only one where there's no connection really between the footing, foundation, and the walls. And here we see the wing walls, cut-off wall in the back, and abutment walls in the front. And there's also corner columns. So basically a box, and the box is, filled with a grid of a geogrid, several lifts of aggregate, and actually chains that kind of hold the whole thing together. Superstructure, basically the box beams, the fascia beams have an integral curb for the guide rail. And here we see the moment slabs. And this is a moment slab that was cast in the plant. It's gone through all the QC checks and finishes and ready to go out to the yard to be stored. Again, this was match cast post tension together, and this project was completed in 21 days. And during this presentation, when I mentioned the time duration for a project, it's road closure to road reopen. So this one was 21 days. Next one we're going to look at is the modular deck type. So again, there's for the abutment ends, there's some match casting and post tensioning, but basically for this one, it's on foundation, it's piles, and there's an abutment pile cap, end walls, some cheek walls, and then the wing walls with the integral curb. And you can see with the steel piling to help with the vertical control, you can see, if I can get my pointer there, on the piles, they basically welded some horizontal elements for the abutment to rest on, so that to help with the stability and vertical control. This is just a close-up of the modular precast deck on, in this case, steel girders. Have to admit that the span of this bridge was about 85 feet, and I have to admit the first time I saw steel bridge girders in my pre-stressed concrete plant, it was a little unnerving, but I got over it, and we've done a fair amount of these. So pretty good product line. But I definitely have to show, as Reid mentioned, that it can be done on pre-stressed beams as well. And these are spread box beams and a big modular piece. And Reid also mentioned that a good accelerated bridge product for the beams is the next beam. So here's a couple next beams. And this is a fascia piece of a modular system that we did down in Anacostia, Maryland, just south of the Washington, D.C. Beltway. And I wanted to show the aesthetics. I mean, this is a form liner with stained stone pattern, and it turned out really nice and very similar to a lot of what you see down on 295 between Washington, D.C. and Baltimore. Again, just to mention, we're back to the wampum job now, and just to mention that form liner is a really good way of kind of inexpensively coming up with some pretty nice aesthetics with concrete. And this is the fascia module at the Lawrence County job being set. You see it's got the integral curve as well for the guide rail. And this project was only a 7-day road closure to open. Okay, now we're going to look at the emulative design. And again, everything so far, and including this project, is match cast and post tension together. You see in the model the different components. You got precast footings, the abutment and wing walls, corner columns, pre-stressed bulb tees, the deck with integral parapets, and the sleeper and approach slabs. So this project was originally a conventional bridge. Originally, it was just 5 125-foot long bulb tees, and it's right next to one of New Enterprise Stone and Lime's quarries. New Enterprise Stone and Lime happened to be successful on the contract, and they basically came to us and asked about getting together with them and going to District 9 and discussing a VE, value engineer, possibility of doing this in total precast. And so, long story short, that's how it ended up. So there you see the abutment sections. You can see the post-tensioning, traverse post-tensioning ducts. And here's an example of one of the abutment walls being match cast onto a corner column. And match casting is just using a piece that we've already casted, and that actually becomes a form or one of the forms for the next piece, so that we get a perfect fit. And so you can see the reinforcing, the post-tensioning ducts are the white pipes here. And then on the left, you can see all the NMB splice sleeves. And just kind of a close-up on the NMB splice sleeves. This is the connection, and it's a pretty common connection from wall to wall vertically, or wall to foundation. In this case, it's wall to foundation. And so basically, vertical piece of reinforcing bar out of the footing into the sleeve. And to make the connection, grout is pumped from the lower tube. And when the grout comes out of the upper tube, the connection is made. So here's an example of a dry fit in the yard. We typically dry fit, most all of our total precast components. Lots of times we're just dry fitting a component to a component. Sometimes we do the whole structure, but this is the Ashcombe Bridge. And just a note, you can see all the tubes at the bottom of the panel for the NMB splice sleeve connection. And another advantage I'll just mention, with lots of templates, care, but also 3D BIM technology, with this project, and then there were 6 other bridge structures over I-78 in Berks County. Altogether, there was about 6,000 of these NMB splice connections. And so by dry fitting them all in the plant, we had 2 issues, not too difficult to overcome, but we found them all in the plant, so they were not an issue in the field. Here's an example of a modular deck bridge that the whole thing is dry fit together at the plant. So we're back to the Ashcombe Bridge, and we're setting the foundation pieces. You can see that they are match cast and post tension together. There was also a question from last week's presentation about the subgrade for a total precast, specifically for the foundation pieces. And here you can see this is an aggregate subgrade, so a lot of care was taken to make sure that that it was pretty much perfect, and so that there was a good uniform bearing for all of the pieces. We'll talk about another type of subgrade in a little bit. So basically erecting this in the field, contractor was able to get an abutment end per day. So that part of it went up pretty quickly. And here we see all the beams on, and we're starting to set the decks. Closer look at the decks, I want to point out a few things. The first thing that you see is post-tensioning ducts coming out the end, and an exposed aggregate keyway finish for the grout between the pieces. Then you see these openings in the deck, and when you look over at one of the bulb T girders, you can see that the composite steel is bunched together to match up with these openings, and that's how the composite action is handled. All the way in the right-hand corner, you see this is lined itself up to be a ultra high performance closure pour. And then you see there's 6 leveling devices, which we can kind of preset and get ready at the plant where we're doing dry fit so that they're very close. And so that's a helpful aid in the erection. These precast decks have the integral parapets, and one lesson learned from a design standpoint that I want to point out here is that the fascia beam is now being directly loaded, whereas in a conventional bridge, the deck gets poured and you have the advantage of the composite action, the composite steel on the top of the girder with the deck slab prior to the parapet being poured. In this case, we're loading it right away. So that's just a design consideration that needs to be taken care of when you're doing integral parapets. Okay, this project was completed, road closed to open in 54 days. And I will say that about 14 of those 54 days were some issues with the ultra high performance, but were taken care of. Didn't turn out to be an issue at all. But there was 14 days of downtime where this project was really about 40 days road closed to open. And the last one we're going to look at is the PennDOT standards. This is about a 130-foot span bridge over in Lehigh County over I-78. About 150 pieces of precast altogether. And so we're no longer match casting and post tensioning. So the basic connection, you can kind of see it down in the footings, is basically a keyway that gets grouted. You can't really see it too well on the walls, but that's also the connection with the walls. And NMB splice sleeves to the foundation and all the vertical connections for the walls. One of the other new elements with this are the beam seats. So these are precast beam seats. They have leveling devices So each one of them can be individually leveled, which is very helpful, especially when you have multiple wall horizontal joints when you get to the top to be able to make that adjustment. And it works very well. Here it is in the field with both abutments installed, and these precast beam seats that I was just talking about, you can see on the near wall. And this is just an overview model of this superstructure. And you can see the closure pour up the middle, post tensioning, and skipper slabs, approach slabs, all the above. Okay, same bridge, night set with first deck slab. And here we see the deck slab. All the beams are now set. And this project was a 30 calendar day from road closure to road open. All right, now we're going to take a look at about a 2-minute time-lapse video. This was the last of the underclearance bridges in Berks County. There were 6 altogether on I-78. Again, about 130 plus or minus foot span. And we're going to take a look at this time-lapse video. This time-lapse video is on our webpage, PCI Mid-Atlantic's webpage. Probably many of you have seen it already, but it's going to walk through the number of days and all of the activities demolishing and building a bridge. We make a camera adjustment here in just a little bit so we can see the abutment in the foreground a little bit better. You see they're starting to prepare the sub base, and they actually pour a rough concrete slab. This is a project that I mentioned earlier, where instead of an aggregate sub base, they used flowable concrete. So after the foundation pieces are set, there's holes in the foundation pieces, and they get pumped with flowable concrete to get 100% good bearing. So you got the abutments going up, backfilling. You see the beam seats going on. Day 14, we're going to see some beams. When the beams get set, you'll see some black pieces on top of the top flange, and that's a neoprene kind of stay in place form for the haunches that get poured, and that worked out pretty well.
Hey, Greg, I think you've accidentally been muted. Could you please unmute yourself?
How's that?
Got it. Thank you.
Okay, sorry about that. Hopefully that didn't happen after slide 2. Okay, so there's the bridge completed. 40 days, road closure to open. And just to give an idea of the value of speed in total precast bridge structures. So the average of the 6 bridges on I-78 in Berks County, the average day road closure to open, fully erected, open to traffic, was about 43 days. So with 6 structures, that rounds out to be about 9.5 months of construction on 6 bridges. There was another bridge closer to Harrisburg that was being constructed at about the same time frame as these. And excuse me, it's about 13 months. So a similar bridge, about 13 months for one bridge, or about a month and a half apiece in doing an accelerated. So just to give you an idea of the value of speed on fairly good sized bridges, complicated bridges. Okay, just kind of wrapping up a few things here, a few more pictures. I kind of showed this one also in a previous presentation, but just an idea. This is a local amusement park pedestrian bridge. This is the bridge installed, and this is the bridge with all the finishes, just to show some of the aesthetics that we can get with bridge products and form liners and things. So interesting as well that the person in our office that worked with Tekla to do the model and all the detailing for the shop tickets is also one of our field coordinators. And so he actually went in the field and erected this. And so I basically told him if he's got any problems with fit up, he's the one that drew it. But anyway, it turned out really good project. All right, this is a project in just north of the Washington, D.C. Beltway. It's the Cedar Lane Bridge in Maryland. And we started out with this job with 52 box beams. And contractor had an incentive to finish early, and state of Maryland allowed him some flexibility, and he started asking what else could he do in precast. It's a 4-span bridge. We ended up doing the abutment caps and pier caps in precast, and they asked what else can we do. We ended up pouring the sidewalk and ornamental parapets on the fascia beams. So here's the project going together. And the project complete. One other project to throw in, this is the Arlington Memorial Bridge in Washington, D.C., another national monument. We did several rectangular beams and some pretty high-end 42-foot long pre-stressed, all stainless steel reinforcing and pre-stressing deck slabs for the Arlington Memorial Bridge. You can see the Lincoln Memorial in the background. And just to wrap up with some advantages. So advantages to accelerated construction, public and job site safety, reducing exposure to the traveling public. Lots of times, instead of a long phasing, it's a short detour. So it just kind of gets the traffic away from the construction, and that's safer for the construction crews and the traveling public. There's smaller crews, shorter durations. The speed of accelerated construction, that's kind of the hub for most all the other bullet points, but just significant close to open time savings for roadways. Federal Highway Everyday Counts initiative, it falls into that. The reduced environmental impact. So if there's trout streams or other environmental constraints, you can get around those pretty quickly. Also replacing more deficient bridges faster. It's not weather dependent. We've erected parking garages. In fact, we erected 2 parking garages this past winter, not a real mild winter. And so you can do it all year round. And I've heard that time is money. Quality, this is plant cast, precast. There's PCI level 2 and 3 certified precast quality control technicians. It's PCI audited, and there's usually third-party DOT inspectors as well. And we're manufactured under some ideal conditions. Okay, so we can control a lot of temperature, moisture, have more consistent curing, and higher performance concrete. Field operations, less laydown area, less specialized equipment, smaller, less costly crews. And again, it's not weather dependent. And risk management, you just reduce exposure for a number of things. Construction delays, schedule erosion, environmental impacts, I mentioned already, accidents and injuries with smaller crews and less duration, public issues, and also one of my favorites, litigation. Okay, with that, I'm going to turn it back over to Rita, and I thank you for your attention.
Thanks, Greg. That was fabulous. Another great tour of going to the job site today. Last week it was going to the plant. This week it goes to the job site. I have about 15-20 minutes worth of material that I'm going to share my screen. And once we complete, hopefully we're going to try to finish a little bit earlier than last week. We were kind of up against the time clock when we started Q&A. So we're hoping that I'm going to get to the end, which will be hopefully around 20 past, and we'll have, I did see a fair number of questions, so hopefully we'll be able to answer some of your questions before we log off around 1:30 today. And if we do not get to your questions, we did put together all the questions we got asked last week into a document with answers. So we will do the same based on the questions we get from today's webinar, and we will have those available for everybody too. So I'm going to go through additional ABC case studies, but what I will be trying to do is tie in with some resources that are available to you related to the ABC design and things that you would have available to you if you have questions. I do want to also make a plug that we do have a fair number of case studies on our website. So you can go to either PCINE.org, PCI-MA.org, or PCI, and look at project profiles, and you will find a lot of case studies there in case you want to see other examples. I will go through some PCINE technical committee activity, and then finally some resources to conclude the presentation. So with that, I do want to make a note here before I start that a lot of the stuff that I present was developed by the PCI Northeast Bridge Technical Committee, which covers the New England states and New York. It was established back in 1990 as a partnership between DOT producer and consultant. This is just a snapshot of showing you the people that are currently on the committee. We had our 30th anniversary last year, so it's hard to believe 30 years has gone by. And Reid and I, obviously, when the NEBT girder, which he talked about earlier, there he is. He came out to see the first girder since he was involved with the development of the girder and the rest of the committee there. So how do you get to some of the resources that we're going to talk about over the next couple of minutes? They live on my website, PCINE.org. So I do want to note that, because if you do go to PCI.org, you will not find those resources. They are unique to the Northeast region, but are available to anybody that wants to use them. So the next beam guidelines were just recently updated. We will be going through session 3, the updates. So those that are familiar with the girder that want to learn what was changed, I would ask you to try to attend session 3. We recently updated the full depth deck panel guideline last year. I'll talk about that here in a minute. We also have a stay in place deck panel guide. We have a deck bulb T guide, and then we have a camber profile management for adjacent beam guide. And then finally, we also have a resolution of nonconformances and precast concrete bridge element guide. That guide, I do want to note, is similar to what National has for repairs of girders. Ours just has additional information added to it. National will eventually be updating their repair manual too, so hopefully the two of them will be very similar. And then finally, we are working on our accelerated bridge guideline, which was published back in 2014. Committee is currently going through it. We are going to be making updates to it. We're going to be adding some of the newer sections and details that are available based on research. We're hoping to have the document completed by the end of this year, but for those that work in committees know that committee takes a lot of time to try to get everything through. But this document that currently is available on my website is still valid. It's just that we're going to be adding more information to it. And then finally, I do want to note that MassDOT does actually have standards for substructures, and you can download those. Those standards are actually based on the PCINE guidelines. So you can take a peek at that as another additional resource. So as far as different type of decking, Greg did a great job showing you visually some of this. I do want to note a little tie-in here. So stay in place forms are basically a partial deck element that you cast concrete the remainder of the deck out in the field. So we do have a guideline for that. Full thickness deck panel, which has been pretty popular and growing in more usages because of obviously trying to replace and reduce schedules on deck replacements. That deck panel guideline was just updated. And then of course we have decked elements. So whether you're looking at next beam or whether you're looking at deck bolt tees. And then finally the hybrid solutions, which are gaining more popularity. People are coming up with creative ways of trying to get the deck done offline, so to speak, rather than doing it on site. The next beam guidelines, again, we will go through those, so I'm not going to spend time here, but I do want to make a note here that we did expand the FAQs, which happens to be one of the areas that I see a lot of usage on my website, where people are constantly looking at the FAQs. So I do know that it's important. A lot of the updates we made to the next beam guidelines are going to be in accordance with the new AASHTO ABC guide spec. And that also relates to obviously anything that's a decked element, where we talk about the different types of joints that are available. We will cover that and go through some discussion when we go into the next beams. And a note about next beams, because another common question I do get asked is who makes next beams? Hard to believe, but there are actually 14 suppliers in this region. And there's actually more suppliers beyond our region, but just in the Northeast corridor, we do have 14 suppliers of next beams. And the handout that you had with all the producer information, you will be able to locate the plants that have them if you do have questions related to next beams and who's making them. So a couple of examples of some, that jumped on me. Examples of some next beam projects. This was done by Vermont Agency of Transportation. It was a 4-bridge bundle package. These are just 2 of the bridges that were completed. And I just want to show you some of the modifications and things that our producers are getting innovative with, trying to reduce schedules by doing more at the plant. The beam here that's on the tractor trailer is a next beam that's been modified, obviously, with the back wall being cast on, the parapet being cast on, all that done at the precast plant with the intent there of not having to worry about all of that work on site. This project did have liquidated damages, so obviously there was an incentive, and they were weekend closures. So you can see the schedule here. Bridge 15 came in 72 hours versus the 84-hour schedule. And bridge 16 came in at 52 hours versus the 60-hour schedule. So both were met. But again, this modification of the beams, things like this can now be done. Obviously, it's trying for a fabricator, but fabricators can do these type of modifications to obviously help accelerate a project. And again, just a snapshot of this bridge being put together and meeting that requirement. Other examples, this is Bath Viaduct up in Bath, Maine. So this is a large project, a longer closure period, but when you think about schedules for something that's 20 spans, this is a 20-span structure that was a total rebuild. The contractor used a combination of prefabrication and cast in place on site and determined what was going to work best for his project. Project did come in 3 weeks ahead of schedule, so some snapshots here. The shaft was cast in place. The pier caps he actually cast right next to the bridge because they were actually very large, and was able to use that combination to make those piers quickly. And then I do want to note the girders were shipped, 2 girders shipped per day was actually shipped from Canada to Maine. There's a precaster that's right over the border, so it was actually a pretty close ship over. And then also this one actually did a UHPC closure joint. So pretty popular when we're looking at trying to accelerate a schedule. Other examples, Sandy Hill Bridge in Middlebury. This one is kind of a neat project. Original bridge was a 1924 arch bridge that they had to replicate. And It had a 45-day closure. Obviously trying to minimize the closure period because it caused a 30-mile detour. And so obviously hardship for people that were on the other side of this bridge. It is a total reconstruction. Again, pieces were very large on this project. One thing you should be mindful of when you are looking at sizing precast elements, especially for substructures, always have a conversation with fabricators, because obviously if the pieces are too big and not truckable, that obviously will have to be revisited how to break up the pieces. So you can always get good input from fabricators as far as sizes of pieces, where to put the joints, how to kind of lay out those pieces to make them work for a project. We also have done a fair number of lateral slides, whether you're looking at bulb T-type girders or whether you're looking at next beams. Those are all opportunities if you want to be looking at a slide in, or SPMT move can also be considered. All the states in our region have used that technology. This was a project in Connecticut where they built the bridge in 2 half sections, slid each section in a 34-hour period over for the new construction. So certainly something like that is also a consideration. And then for very large projects, obviously what you're trying to do is reduce the schedule as much as you can. When you get into very big projects like the Goethals Bridge, you're looking at potentially lots of opportunity on what could be used from a precast component point of view. So if you look at this project, obviously 7,000 foot long structure, $1.5 billion project. There was 397 bulb tees on that project, 178 feet long. So a common question that I typically get people ask me is how long a girder can we ship? These girders were shipped from Pennsylvania to New York. So if there was ever a difficult shipping route, that would be one of them, obviously in a congested corridor. So 178 feet, common question, what's the longest span? You would have to determine that. This is where you call your fabricator. How long a piece can I ship to this location? They may have to cite the route, determine what would work best. But obviously, if you can get to a one-piece girder, it's going to be a very efficient solution. This also had SIP decking. It had full depth decking. It had retaining wall, button walls, T-wall systems, and you'll see multiple producers. So not uncommon for a very large project. I mentioned full thickness deck panel guidelines have been updated. They were updated and posted last year. What we did on the update is the original document only had post tensioning. We now have a non-PT version of details in there. We also added the UHPC joint, and we also have nominal strength concrete in case you don't want to use UHPC. And we also added a longitudinal panel layout. The reason why we did that was that it was used on a project in Boston. And that was a very, again, short window, very complex bridge. They wanted to use precast decking to accelerate the short closure that they needed, but it was a complicated bridge. One of the things that was unique to that structure is it had a really high skew. I think it was a 65-degree skew angle. It was steel beams, and the longitudinal deck panel layout worked really well in handling those skews. So that would be a good way to consider decking if you are looking at something like that. This is a New York project. New York is actually probably in our region, probably used the most UHPC / precast decking replacement solutions. They have been using UHPC actually for a number of years, I think dating back at least about 10, 12 years now. Other states are using UHPC, but they've probably had the most UHPC examples. This one had a 10-day closure period, which was met. New York likes to grind their decks. There is no wearing course on top, but that was what was used here. And I do want to make a note. Greg actually showed a couple of those examples, but bridge bundling I think is going to continue to grow. There's a big project in Massachusetts that was let, that is actually being fabricated now. But I think you'll see bundling as a common technique to try to get a lot of bridges grouped together to reduce the overall cost. Obviously, scale of economy always is best. PCI had a couple of nice articles about bridge bundling in the Aspire magazine. By the way, you can get the Aspire magazine for free. You can just view it online. Past articles, there's a lot of good information in that publication. And then also Federal Highway has some resources related to project bundling on their website if you're not aware of that. But again, I think that's going to be an area that you'll see growth as far as trying to move projects forward using ABC. Some additional resources for you. PCI just published a transportation resource guide. It's basically compiling all the information related to transportation into one document. You can go to pci.org, look under Design Transportation Engineering, and you'll find the document there. You can download it for free. There's no charge for this. It's basically a catalog of all the available resources. It has an extensive table of contents to tell you what's physically in it. And let's just move through a couple of the pages so you can understand what the value of the document is. First of all, it lists all the transportation publications. So you certainly can look at those. We're going to go to the bookstore. I'll show you them there in the bookstore. But what's nice about this document, if you're on the website and you're obviously live, these actually are hyperlinks. So if you say you want the bridge design manual, if you click on that, it will physically bring you to where it is in the bookstore, and then you would just really need to register and be able to download it. You do need to register to download anything on PCI's website. There is no charge for a lot of our e-version of the documents. If there are some e-copy versions that you would have to pay, and then if you do want hardcover, you would actually have to purchase that. There's currently about 20 publications related to bridge and transportation topics available. So let's go to the bookstore. That's your other way. So if you can't locate that transportation catalog, you could just go right to publications, go to the bookstore, and we'll walk you through, but you'll be able to do the same thing there and document and download the documents that you actually want. I also do want to make a note on the periodicals. There are a fair number of nice bits of information available when you start looking at these documents, whether you're looking at Ascent, Aspire, or PCI Journal. I also want to note that Reid is always looking for new projects to put in Aspire. So if you do have a nice project that you think would be worthy of getting published, you may want to reach out to him. So he's certainly looking for new material. So here's what the bookstore looks like. You can sort by clicking transportation infrastructure. It will filter all the transportation related documents. And from there, you can click the one that you're interested in and again, sign in and download it. Going back to the catalog. Now in the catalog, the second half of that catalog talks about not transportation, but educational opportunities. So the thing that's new is the PCI e-learning center that's just been recently updated, much more user-friendly. The older version was okay. But what this catalog will offer you is enlist you all the transportation courses that are free. These were developed with assistance from Federal Highway, and they were written by a team of experts. You'll have basically the theory, design steps, general information on how to design bridge structures. When you're in the catalog, again, if you click on the class that you're interested in, it will hyperlink to that actual class. So it's a direct link, again, quick way to get there. And again, there'll be general information in the catalog. The design discusses each of those classes and what's in them. If you don't have the catalog, you again can get to these classes through PCI's website. You would go to the education tab. And under the education tab, it lists all the educational opportunities PCI offers you. First of all, we have monthly webinars. Those are free or on demand. We have what's called the PCI Academy. That's a live class. And then finally, there's the e-learning center, which I'm going to go through here in a second. That's again on-demand training and free. And Greg was good enough in making a plug for lunch and learns. We do lunch and learns, whether they're live or virtual, they're free. So reach out to Don or I if you want something for your entire office. We can set that up. And then finally, there is plant tours. So this is what it looks like online. If you're going through the website, you click on the transportation classes. And if you go over to the alphabetical and you sort that, it will sort out all the classes in order. So you can look at them in an orderly manner as far as what you may want to consider taking. I do want to make, oops, that skipped on me. Want to make one quick note here. Reid is teaching us a lot of good information on the basics of pre-stress. If you've never had pre-stress concrete design, or you have a new hire, PCI does have a 6-module 90-minute class that's for free, and you can download those and follow along. It's actually pre-recorded. This is what the classes look like. If you sort them, this is the T100 series, which basically is all the basics. You click on the one you want. You do need to register. If you want PDH credit, you do need to register. So register, log in, and then you can start taking the class. This is what the class looks like. It has a right navigation. And basically you can stop and start. It's about 60 minutes. It's self-paced. It's a talking module. There's tests along the way. You do need to take a test at the end to complete to get your PDH credit. And you can download the notes on demand so that you'll be able to follow along as the modular is speaking to you. And then finally, I do want to note, if you're working on a project, you need help, don't be afraid to reach out to us. You can reach out to the plants if you're looking for budget, schedule, design directly, or you can reach out to the regional association if you're looking for something specific that the regions can help you with. There are other regional associations. I know we have people that have signed in from beyond the Northeast region. If you go to the regions, you can find all the other regional reps there, and you can connect with them directly. And just a plug for our next session, which is next Tuesday, again, 11 to 1:30. We will be continuing. I'll do another brief on the updated resources, but we will be talking about lateral stability, girder repairs, UHPC, and then Mike Culmo will be doing an update on the next beam, and we will have a roundtable discussion. So that is my last slide. We're right about a minute or two over, but we do have time to have our Q&A, and I'm gonna kind of open it up for a question and answer. And I know, Dawn, I don't know if you have the Q&A questions. We can open up the chat, and I'm going to stop sharing here. And
I think Reid and JP has been logging the questions. I think we have a handful if we want to go into those discussions, and Greg's here as well, so he can definitely chime in from a fabricator standpoint. So JP, do you want to kick this off with our questions, and we can have a roundtable here discussion depending on what that question is?
Sure, Don. So I think the first question is a good one for Reid. The question is, on slide 24, the top steel calculation is shown as AS equals T over FS, where FS is limited to half the yield strength. Can you clarify if the top pre-stressing strand, in the case of top debonding strand, I believe, can be used in this AS, and that 30 KSI is still the allowable steel stress?
That's a good question. The specs are not particularly clear, if I recall. It's been a while since I've run through that. I believe that in the past, what I have done is include the strands, but at a grade 60 working stress for computing that. I don't know. Have you done that too, JP? Or
yeah, it's a little bit of double dipping, right, Reid? Because your stresses on the end are already related to the full stress strand up top. So if you also include the area steel at half the yield of a 60 KSI as allowed by AASHTO, it works. Is it conservative? Perhaps, but that seems to work.
but it works. You're addressing steel or strains and that sort of thing. So I think it's defensible.
Okay. One question came in about, are drape strands utilized in post-tensioning applications? And if so, would there be significantly lesser safety considerations? I'll say that in post-tension concrete segment construction, deviator segments or like Diablo deviators are common for basically a heart point in the span. And then for post-tensioning, it's typically a parabolic profile with post-tensioning ducts rather than a hard drape point. I don't know if you guys have anything to add to that.
I think that's a good, hopefully that addresses the question. Sounds good.
Okay, next one that came in was more of a statement, but it was that hold down locations are typically based on the beam length, so they do use 0.4 and 0.6 L. I think your statements, Reid, were very appropriate that yes, you may use 0.4 L, you may use 0.6 L, but in terms of the bed layout, sometimes the supports of the soffit require that it becomes 0.39 L, 0.38 L. You might just have to shift a little bit. Doesn't usually have a huge impact on the design, but there's some states I believe use plus or minus 5 feet as kind of a go by in order to work with the means and methods. So I don't know, maybe Greg, you have something to add to that?
I completely agree with everything that you said. There's got to be a little bit of flexibility to be able to move a little bit. Yep.
Okay.
One more
for
question. I was just wondering, follow up there with Greg. What's the spacing of your points? For example, I mean, you have to have pins or whatever that are holding the hardware for your hold downs. Is that every foot or?
That's a good question.
Okay.
I want to say yes.
Yeah.
I'm trying to think of the spacing of our cross members. It's either it may be like 18 inches, but
Sure.
yeah, there's something. Yeah.
Yeah, I was just thinking of an example for the listeners that yes, indeed, that there are physical locations where you can have a hold down. It's not just anywhere you want. It's not a sliding thing. Typically, it's a pin that goes through.
But the point that moving it a little bit is really so infinitesimal to the design. Right. So. Yep.
Very good. Which is
I
the
guess
thing for splitting them. If you have to go to 2 hold downs, you're moving it a little bit, but it has very minor impact on the designs. Very.
I was going to say also that the soffit is supported by sleepers usually, which are spaced at 4 to 5 feet based on the manufacturing of the soffit. So, that could also limit your hook point. So the whole point is that tolerance should be allowed for draping. I think that's the takeaway. One more for you, Greg. Is crushed stone backfill, is that a standard that you see in your ABC applications that you showed so well?
Yeah. Yes. Okay. Yeah. And I'm not sure where I got muted during the time lapse, but I made a point in there that there was an example because there was a question earlier about the foundation subgrade. And in the time-lapse video for the Berks County job that we were looking at, that was one where they used flowable concrete. There were holes in the foundation pieces, and we set them on shims, or you could use leveling devices, but you get them to the right elevation, and then you pump the flowable concrete in until it comes out all sides, and you get your good bearing. So
that's great. Okay. One more for you, Reid. Let's see here. Deck slab shrinkage effects, are they considered in your Camber calculations? I think maybe that might be, are you considering all the shrinkage in your Camber calculations potentially in service?
Yeah, typically when we're doing Cambers, when you're doing calculations are, as I tried to highlight on the first few slides, very much estimates. You can certainly include all the parameters as much as you want to try to refine that estimate, but things like modulus and all, they have very large spreads unless you're getting a measured number from a prestressor. So I'm not sure that degree of refinement would be all that helpful, but you could certainly do it. The multiplier method that I showed does not include consideration for differential shrinkage causing modifications to the cambers.
Well, I think I'll add to that just a little bit because you mentioned in your slide, but I think really want to drive home that, once an 8-inch deck is cast on top of these girders, they don't change much. It's a very stiff deck element with reinforcement. If there is minor differences in deck shrinkage numbers, what have you, those multipliers really don't apply to the building multipliers after the deck is cast, really don't apply to pre-stressed design of bridge girders. So,
yeah, good point.
Okay, the last one is a great question for you because I know you use it a lot. What experience do you have using PG Super in design?
PG Super?
PG Super.
Well, I haven't actually used it all that much. I've used PS Beam a little bit more, but PG Super, as far as I know, I actually have a copy. I've downloaded it. I'm getting ready to use it in the next month or two, but I haven't done much lately. Sorry about that, but I don't know if you have it.
Well, I would say that the originator of that program, or at least the caretaker of that program, is a very, very capable precast prestress designer and engineer. So I would say Rick Bryce he's also the chair of the Lateral Stability Committee and with WASDOT. So it's a great program. It's state of the art.
And he keeps it updated. He's on T10, or is at least certainly very involved with T10, the AASHTO committee that is the caretaker of Chapter 5. So he certainly implements correctly whatever is coming out of T10 that needs to be updated. And it's done right away, I would expect.
All right. Well, we sure appreciate everyone attending and sticking with us. And we really hope that you can join us for the conclusion of our 3-part series, which is next Tuesday, 11 to 1:30 Eastern Daylight Time. And we'll have an animated discussion, I'm sure, of precasters on a panel of submitted questions and topics that you've already submitted, and hopefully we'll be able to open that up and have you submit questions live during that panel discussion. And JP will be talking about ultra high performance concrete and a few other topics. So thank you all. We're going to conclude now, and we appreciate
Don, I do want one quick note. A lot of people kept asking about the notes.
Sure.
Hopefully you got them. I couldn't tell. I know there were some people that said they weren't. But I put a Dropbox. There was also a WeTransfer link. Hopefully one of those worked for you. But we will be posting everything once all the recordings are done. We will actually post the recordings with the Q&As so that people can look at those at a later date if you still didn't get them. And there was also a question about last week's session. Those will be available once the entire seminar series is complete. We will have the whole package of information available to everybody that attended, that can go back and listen to those at a later date if you missed it. But we again thank you for obviously your patience with the notes. So we couldn't seem to be able to post it into the Zoom link. It was not for some reason going in. So
yeah, good. All right. Well, thank you, everyone. We'll make sure that we make all the materials available, as Rita said, once the entire program concludes next week. All right. Have a wonderful rest of your day, everyone. Thank you.
thank you.
Thank you.